Okay, now we're jumping into rational functions. We'll start with some true-false questions just to make sure we have a conceptual understanding of what we're doing here. True or false, a whole and a vertical asymptote can occur in the same function. Well, this is true. I can imagine a function where I have something like this, a whole here and a vertical asymptote here. So that's perfectly fine. Now let's talk about 2. A whole and a vertical asymptote can occur at the same x value. That is false. At any given spot, I can either have a whole or a vertical asymptote. I can't have both. I can't even draw it. It doesn't make sense. All right? And in fact, that also goes for a 0. A whole, a vertical asymptote, and a 0 cannot coexist at the same x value. They can coexist in the same function. We see that all the time. But they cannot coexist at the same x value. You can only have one of these 3 at any given spot. A whole and a 0... Oh, well, I just kind of gave this away. A whole and a 0 can occur at the same x value. That's false. So you can imagine, and sometimes this confuses people a little bit, I have something like this, where there is a whole at the x-intercept. Well, this x-intercept does not exist because there's a hole there. It does not exist. If the value doesn't exist there, we can't have a 0 there. So you can only have one or the other. All rational functions have either a whole or a vertical asymptote. I think this will surprise some of you that this is true, because a rational function is going to be undefined somewhere. All right? They're not continuous. Okay? So there's going to be some spot. Otherwise, it would just be a polynomial function where we either have a whole or a vertical asymptote. They have to have one of the two. If we don't, that's fine. It's just not a rational function. It's a polynomial function. All right, now let's dive in. For each function below, determine all the wholes and vertical asymptotes. All right, well, anytime I have something in the denominator, I'm going to get one or the other there. So x minus 2 cannot equal 0. That means x cannot equal 2. This only exists in the denominator. So this is a vertical asymptote because this factor only exists in the denominator at x equals 2. All right, here again, I have something in the denominator, x cannot equal 0. X is only in the denominator, so that means I'm going to have a vertical asymptote at x equals 0. Now we're moving on. All right, well, I know x cannot equal 10, and x cannot equal negative 12. So at each of those spots, I must have a whole or a vertical asymptote. Here, I'm going to have a whole because we'd get 0 over 0 here. So we're going to have a whole at x equals 10. But x equals 12, that doesn't occur up here. I don't see that in the numerator. So I'm going to have a vertical asymptote at x equals negative 12. And just so we're clear, there'd also be a 0 to this function. X plus 8 only occurs in the numerator, so I'd have a 0 at x equals negative 8. 0 there, okay? All right, number 4. I want to be in factored form anytime I'm looking for these. So the first thing I'm going to do is convert to factored form up top. So I'm going to get x plus 2 x. Wait, does this factor? Yeah. Yes. And we get x minus 4. X plus 2. Okay, well, here I have this x plus 2 on the top and bottom. So that's going to be a whole at x equals -2. And a vertical asymptote. Well, this x equal or x minus 4 only occurs on the bottom, so I'm going to have a vertical asymptote at x equals 4. I know I didn't ask, but there's a 0 at x equals -10. All right. Let's factor this. Again, this is in standard form. I think some of you will struggle to factor this. We need to put on our critical thinking caps. So I'm thinking about what multiplies to 0 but adds to 4. Well, that's going to be x plus 0 and x plus 4. I don't really, I could write it like this. It's kind of silly, right? We're not going to write it like that because we don't need to write plus 0. We know that. So it's going to factor like this. Well, here, this is where we have to be smart math thinkers. 3x equals 0. I'm going to end up with x equals 0 on the top and x equals 0 on the bottom. So I'm actually going to have a whole at x equals 0. And I'm going to have a vertical asymptote at x equals, well, this only exists on the bottom, -4. All right, now we're really talking. All right, we have a same factors on the top and the bottom, just with different degrees. And maybe it's a little easier to just write this out. Let me switch colors. I could rewrite this in expanded form as x plus 4 times x plus 4 times x minus 3 all over x plus 4 times x minus 3 times x minus 3. Well, I want to think about this. If I cancel I want to come over here first. If I cancel these out, right here, these x minus 3s, I'd still have this on the bottom. And the bottom only. So now when I have something on the bottom only, well, what does that mean? That means it's a vertical asymptote. So I'm really going to have a vertical asymptote at x equals 3. Here, well, I don't, if there's might be some temptation to cancel that out and say, oh, I have a 0 there. No, because if I substitute 0 into, -4 into x, I'm going to get 0 over 0. And that is going to result in a whole. And that goes back to this rule. Let's see if it's still on my screen, that we wrote all the way up here. That if the degree of the denominator factor is larger, then we're going to end up with a vertical asymptote. All right, back to where we were, though. All right, same thing. I've got some stuff existing on the top and the bottom. Well, let's start with this x minus 10. The degree of the factor is larger in the denominator, so I'm actually going to have a vertical asymptote at x equals 10. Well, here I still have this x minus 2. It only exists in the denominator, so I'm also going to have a vertical asymptote at x equals 2. I don't have any holes. I have 2 zeros, though. All right. 8. This is in standard form. I really want to factor this. First, so I'm going to do x. Factor out this x, so we get x squared minus 9x minus 90. I know this factor is x plus 9, x minus 9. I'm not done factoring this. I can factor this quadratic right here. So I can say the p of x equals x times x plus x minus, no, this doesn't work. Can't factor that. Cannot factor that. I actually am done factoring this. There's nothing that multiplies to -90 and adds to -9. So I can just leave this be. And so I'm really just focused right here on these. Remember, x cannot equal 9. X cannot equal -9. So these don't exist up here. These don't exist up here. So these have to be vertical asymptotes. I have a vertical asymptote at x equals 9. Maybe I'll even do cool notation like this. I have a vertical asymptote at x equals positive and negative 9. All right, let's hop over here. Well, I have this 2 on the bottom, and what does that mean? Well, there's no x. If there's no x in the denominator, then there's no value of x that's going to result in dividing by 0. And I think it helps to get back to the foundations. If we're never dividing by 0, we're never undefined, which means it's continuous, which means it's a polynomial. This is not a rational function. This is a polynomial function. Because I could easily rewrite this as 1/2 x squared plus 5x plus 6. This is not a rational function. There's vertical asymptotes, none. Holes, none. Because this is a polynomial function, which means it's continuous, right? It's going to go like this. The domain is negative infinity to positive infinity, unless we say elsewise. All right. So that's a little bit about holes and vertical asymptote, places where the function is undefined. Now let's talk a little bit about the end behavior of rational functions. All right, true or false? A rational function cannot have both a horizontal and a slant asymptote. That is true. We can only have one or the other because a function cannot be going like this if it's somehow also going like this. All right, so we need to have one or the other. That is true. True or false? If a rational function has a horizontal asymptote, then the function increases and decreases without bounds. The output of the function will approach the horizontal asymptote. So let's just sketch that out. Let's say we have a horizontal asymptote. So as we increase without bound and as we decrease out without bound, do we approach that horizontal asymptote? Absolutely. The horizontal asymptote is the describing the end behavior, essentially. We're getting closer and closer to that, but we'll never reach it. All right, true or false? If a rational function has a slant asymptote, then its end behavior will always replicate a linear function with a positive slope. Well, let's imagine this slant asymptote. And this seems pretty good. It seems pretty true to me. But wait, a positive slope? No. What if I had a negative over a positive? So for my function, well, then I wouldn't get it. Let's just say I had negative x squared over x. Well, negative divided by a positive is a negative, so my slant asymptote would be a negative. So this word positive makes this false. All functions have either a slant or a horizontal asymptote. All functions? No, that is just not true, right? I mean, a linear function doesn't. Bam. A quadratic function doesn't. Bam. Any polynomial does not. So that is certainly false. All right, for each rational function, determine if it has a horizontal or slant asymptote and then describe the end behavior using limit notation. All right, this is going to be a lot of work. All right. Well, a slant asymptote occurs when it is one larger than the horizontal asymptote. I'm realizing I also forgot to do this in the mind map, so we'll cover it a little bit here. We're going to distribute this into factor or standard form, so I'm going to get x squared minus 11x plus 24 all over x plus 4. Well, the degree of the denominator is one larger. That means I'm going to get a slant asymptote. I need to do some polynomial long division. If you're Chris, you're probably going to do synthetic division. But I believe in polynomial division because it works every time. I'm going to ask myself, x times what is x squared? Well, that's x. Now I'm going to do x times x is x squared. 4 times x is 4x, and subtract these. These cancel out. I'm left with negative 11 minus 4, which is negative 15. Please take your time to thinking about adding and subtracting with these negatives. Negative 15x. Yeah, I got to drop down this 24, but it doesn't really matter to me because x times what makes negative 15x? That's negative 15. And so I know I have a slant asymptote at y equals x minus 15. As soon as I get a constant here, I can stop. All right, next one. Again, I'm going to convert this to standard form real quick. X squared plus x minus 56 all over negative 3x cubed. Well, when the degree of the denominator is larger, then I'm always going to get a horizontal asymptote at y equals 0. All right, number 3. I have the same degree. So that means I'm getting a horizontal asymptote at a over b, where a and b are the leading coefficients. Negative 6 divided by 3, well, that's just negative 2. So we have a horizontal asymptote at y equals negative 2. Last one, again, I'm going to end up with a slant asymptote because the degree of the denominator is 1, exactly 1, larger than x, or the denominator. So I have negative 4x squared plus 2x minus 8, all divided by 2x plus 1. All right, so 2x times what makes negative 4x squared? Well, that's negative 2x. So we get negative 4x squared. 1 times negative 2x is negative 2x. And I'm going to subtract these. These cancel. 2 minus negative 2. Again, we got to have this. That's 4x. 2x times what makes 4x? That's positive 2. As soon as I get a constant, I can stop. We have a slant asymptote at y equals negative 2x plus 2. All right. Moving right along. Thank you so much for watching these videos and studying. For each of the following rational functions, write a limit statement to describe the left and right end behavior. End behavior. So as we approach go towards the left, so as we decrease without bound, we have a horizontal asymptote. So we're clearly just going to approach that horizontal asymptote. So we can say the limit as x approaches negative infinity, the f of x is approaching 1. That same thing is going to happen when we approach positive infinity because we have a horizontal asymptote there. All right. Now we have to do number 2. Again, I have a horizontal asymptote. These are pretty easy. So that means both when I approach the left or negative infinity, that I'm approaching the output of 2. As limit approaches positive infinity, the output approaches 2. Think about it. I'm getting closer and closer to 2 as I head towards positive infinity. I'm getting closer and closer to 2 as I head towards negative infinity, but I never ever get there. All right, now we have some equations where we need to do it. Well, okay, these are the same degree, which means I'm going to get a horizontal asymptote at a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. So we're just going to have a horizontal asymptote at 2/3. So we can say the limit as x approaches negative infinity, the h of x is approaching or equal to 2/3. I could say the limit as x approaches positive infinity, the h of x is equal to 2/3. It should be the same for both when we have a horizontal asymptote. All right, in this one, we got to be careful. What's the degree here? The degree of the top is 3, or no, it's not, is 2. And the degree of the numerator is 3. Anytime we have the degree of the denominator being larger, then we always have a horizontal asymptote at y equals 0. So I can say the limit as x approaches negative infinity, the k of x is equal to 0. The limit as x approaches positive infinity, the k of x is equal to 0. All right, now we have, oh man, okay. Did not, all right, this isn't really, well, all right, let's just get into it. Here the degree is 2 higher, which means I get a quadratic asymptote. And because this is negative, it's going to be a concave down quadratic asymptote. So the end behavior is going to represent this, because to the fourth divided by the second, and we have a negative leading coefficient. So our end behavior, it's just like a polynomial function, right? It's going to represent this. So we can say the limit as x approaches negative infinity, the r of x is equal to negative infinity, because we're going down forever. We can say the limit as x approaches positive infinity, the r of x is equal to negative infinity, because we're going down forever. Remember, when we have quadratic end behavior, then these should be the same, so that checks out. All right, we have a degree of what? 1, 2, 3 on the top, a degree of 2 on the bottom, so we're 1 higher. We're going to get a slant asymptote. Let's look at, do we have a positive slant asymptote, or do we have a negative slant asymptote? Well, this is a positive divided by a positive, so we get a positive slant asymptote. So the limit as x approaches negative infinity, where are we headed? The m of x is headed towards negative infinity. The limit as x approaches positive infinity, where are we headed? We're headed up. So we're headed towards positive infinity. All right. Number 7, write a limit statement describing the output values of the following graphs and verbal descriptions of the input values. Okay, the input value decreases without bound. So as we decrease without bound, we're headed this way. And where is this function headed? Well, the output is clearly headed towards the negatives, or negative infinity, because this is a slant asymptote, linear slant asymptote. So we can say the limit as x approaches negative infinity, because it told us decreases without bound, the f of x is equal to negative infinity. This time we're saying as the value increases without bound. Let me switch to red. So as we head this way forever, what's happening to this function? What's a horizontal asymptote? So it's just approaching that horizontal asymptote. So the limit as x approaches infinity, the g of x is equal to, where's the horizontal asymptote? It's at 1. All right, now let's talk about approaching from the left and the right. Number 9, we're going to use this graph right here. As we approach 2 from the left, so as I approach 2 from the left side, where am I headed? I'm headed towards negative infinity. As I approach 2 from the right, as I get closer and closer to 2, where am I headed? I'm headed towards positive infinity. All right, as we approach 3 from the left, well, there's a horizontal asymptote at 2. What's there at 3? It's a hole. And what would the output of that hole be? Well, it would be 3. So as we approach 3 from the left, we're definitely getting closer and closer to 3. As we approach 3 from the right, again, we're just getting really, really close to that output of 3. Over here, as x approaches 5 from the left. Again, it's a hole. So I'm getting really, really close to this. Getting so close, so close. Can't get there, but where would we be? We'd be at -2. What happens as we approach 3 from the right? Well, what do we have here? We have a vertical asymptote. So I'm coming from the right side, heading towards positive infinity. What happens as the k of x approaches negative infinity? So what happens as we go this way forever? What's our end behavior? Well, we're going up. So this is going to be positive infinity. As we head towards negative infinity, where is this graph headed? Well, it's headed down. Positive infinity. So this is heading down, so it's negative infinity. All right, and I will do another video